ladies and gentlemen, class recording has started. So, section 4.3 deals with relative motion. And it is my hope that by the end of this discussion here, you will see that the ideal of relative motion is no different than the things we've been talking about for the last week dealing with vectors. The only thing that changes is that now, or before, all of the vectors that we drew had units of meters because they were distances. Today, they become velocities. It's the only thing that changes, okay? That now we deal with things that are in meters per second as opposed to meters, okay? We start off this discussion in one dimension. And a lot of you are familiar with these concepts of relative velocity in one dimension. If you've ever been to the airport and you've walked on one of those moving sidewalks, okay? You know what I'm talking about at the airport? All right. So, let's take this example right here. So here's a picture of you standing next to a train, and you're watching the train go by, and as you watch the train go by, you see a person walking in one of the train cars from the back to the front. And so later on, your manager person or whatever says, "Hey, did you see so-and-so?" And you say, "Yeah, they were on the train." And for some unknown reason, I don't know why, they might ask, "Well, how fast were they going?" Okay? So, just, I don't know why, but. And the answer is, it depends, right? It depends on what?
Relative to who?
Exactly, right? It depends on our frame of reference. It depends on relative to who, okay? If they ask you how fast that person was going, you would have to account for two factors, right? You would have to account for the fact that that person is walking, but also you have to account for the fact that they were walking on a train that was already moving, right? If somebody else was inside of the train car with this person, and that person walked towards them, their description of that motion would be different because the motion of the train is irrelevant to that person because both the person walking and the person sitting on the train have that same train factor counted already, and they don't have to take care of it. Does that make sense? Okay. So, long story short, right, if we asked you how fast this person was walking, according to you, what would you say?
151. According to the person on side?
According to this person right here.
16.2.
We have to take into account
150.
both how fast this person is going on their own, plus how fast the train is going. So we just add those two together, and we get 16.2.
It's a slow moving.
But if we talked about this person, right, and now they're moving in the other direction, okay, even though they are technically facing towards the left, right, their motion combined with the motion of the train, as you watch them, which way would you see this person go? Going towards the right, okay? Because yes, they are walking towards the left, but when we take into account the fact that they're also moving on a train that's going towards the right, now we have to take both of those into account. So mathematically, what would we do here? We just subtract those, right? You know, that now we take the negative part, you know, the negative aspect of the person's motion into account, and we subtract them, right? So somebody asked in the previous class, well, what would happen if the person was walking at 15 meters per second? And the answer then is what? What does it look like that person is doing? Nothing, right? What's a practical example of that? Treadmill, right? You on a treadmill is a practical example of relative velocity adding up to 0, right? You're running at, whatever, 6, 7 miles per hour in one direction, but the treadmill tread is moving at 7 miles per hour in the other direction. Those two velocities cancel out because they're in different directions, and we add up to 0. Okay? Good there? How does this relate to what we've been doing so far? It's vector addition, just not exactly the same kind of vector addition that we've been doing for the past week. For example, the person walking has a certain vector, right? And we said that that vector was 1.2 meters per second, and it's in the positive direction. Okay? To add vectors together, how do they have to be lined up? Head to tail, right? So we take the velocity of the train and we start it where the velocity of the person walking ended, right? And then the vector sum is the one that we draw from where to where? Beginning of the first one to the end of the last one, right? In this case, it would start here and go all the way here. Wouldn't be crooked, but it would be that way, right? It just so happens that now in this situation, when we're in one dimension, right? Because they're both in the same direction, how long is that purple line going to be? 16.2, right? The process isn't any different. We're still adding vectors together, but how we describe it in one dimension versus two dimension makes it a little bit different. Okay? Does that make sense? Okay with that? Okay. How does it relate to what we're doing now? Well, let's take a look at this situation. Okay? Now, a different railroad worker, because they're wearing something different, is on a train, but instead of walking through one of the cars, he's climbing up a ladder that's along one of the side of the cars. All right? So, his velocity looks like this, right? But what else is going on while he's climbing up the train? Train's moving as well, right? Train's moving in this direction like this, okay? What is the combined effect of those two motions going to produce? If you were watching this guy, right, what would you see him doing? Going up and to the right. And that means that the combined effect of those two would look something like this, right? That's the combined effect of moving up and to the right at the same time. Are we adding vectors together here? Yeah, right? How are blue and red lined up? Well, yes, but more importantly, how are they lined up? They're lined up head to tail, right? It's just in this case, it's not a straight line, right? And then the sum of those vectors we draw from the beginning of the first one to the end of the last one. Does that make sense?
Wait, but don't, like if you add the blue and the red together,
yep.
Is that going to be the exact same length as purple?
Yes.
Really?
But it's not, adding blue and red together isn't just adding the numbers together, right? That works when we're in one dimension like this, because it's all a straight line.
Yeah.
But in two dimensions, the purple represents red plus blue. But we don't just add the numbers together, right? That's why it's, velocity 1, but we draw the little arrow over top of it. Plus velocity 2, but we draw the arrow over top of it. Okay? Julie, go ahead.
So the only time that you can just add the vectors together is when it's just the same, they're both going the same direction.
So we would say, well, yes, except for, okay, so Julie, like in this case, right?
Yeah.
On the second example that we looked at, this one,
Yeah.
okay? So here's two vectors, right? So we start off with this one, right? This is still the velocity. Sorry. Let's see if this works. Nope. Okay. This is still the velocity of the train. That still represents 15 meters per second, right? But now, this person, they don't have them lined up the way I would line them up. Okay, actually they do, but that's okay. We would start the second one at the end of the first one, right?
Yeah.
This is still 1.2, but now it's 1.2 which way? To the left, right? So the vector sum is still the one that's drawn from the beginning of the first to the end of the last.
Yeah.
Okay? In this case, though, they're not exactly in the same direction, so mathematically, what would we do here?
Subtract.
Subtract, right? But that's still adding, we're just adding a negative number.
Okay.
Does that make sense?
Yeah.
It's still drawing a vector from the beginning of the first to the end of the last. When it's in one dimension, we can just kind of do math, we can just kind of do plus or minus to figure it out, right? But when it goes into 2 dimensions, the process is still the same, but how we handle that mathematically is a little different, right? So how would we do this, right? If this is still 1.2 that he climbs up, or sorry, 1.2 that he climbs up the train, and this is still 15, right? Is the purple going to be 16.2 this time?
No.
No, right? How would we find the purple one?
Pythagorean.
Use Pythagorean theorem, right? And then we could also find out the direction that it's going as well by finding that angle. Okay?
So I get that, but then wouldn't you not say that it's v1 plus v2? You would say it's technically the square root, the square. I don't get why you'd say plus, because you're not adding them.
You are adding vectors together. You are finding the vector sum. It's the same idea, but that's the whole point of this chapter. When we added velocities before, we just added them up because they were all on the same line.
Yeah.
But when we have something that's in 2 dimensions, you can't just add the numbers together because you also have to take into account the directional aspect.
Yeah.
Okay? That's the whole point of this chapter, is taking those ideas that we learned in the first couple chapters and applying them now to 2 dimensions. Okay? It's not just the same as adding them together. It's just not how it works, right? The combination of this person moving up 1.2 and moving to the side 15 does not yield 16.2 in that direction. It's just not how it works. Okay? But that's the whole point of the chapter, is how do we deal with that in 2 dimensions. Okay. All right, we good there? All right. So let's take a look at this example right here. Okay? This is sort of a classic example that shows up in this section in all kinds of physics books. So you got a boat on a river. Okay? Before we talk about this problem specifically, right? Let's say, all right, you got this river, okay? And here's you and your boat, okay? And it says here in this problem that your boat can go 6.1 meters per second, okay? Now, let's say over here, there's a fabulous picnic area here, and you want to take that special someone across the river to a nice secluded picnic area to have, you know, a romantic lunch, whatever, you know, right? Here, we'll give a little ambiance here, right? So there's a little flower action right there. You know? There's like there's like woodland creatures, you know, like
What?
squirrels. It's a squirrel. It's got a big tail, you know. So it kind of looks like a turtle squirrel, kind of, you know. But I mean, everything's more romantic with woodland creatures, right? I mean, like turtle. So anyway, so you got your boat, all right, and you got to cross the river to get to the romantic picnic area, complete with woodland creatures. Okay? So the river is flowing in this direction. If you're on this side of the river and you go, oh, picnic area, I'm just going to go straight across the river. You take your boat, right? You go across the river. Are you going to end up at the picnic area?
No way.
No, right? You got to take into account both the motion of this boat plus the motion of the water, right? The combined effect would be the vector sum of those two. Okay? So here, right, it says you're riding in a boat whose speed relative to the water is 6.1 meters per second. That means the boat can travel 6.1 meters per second. The boat points at an angle of 25 degrees upstream on a river flowing at 1.4 meters per second. So two things. What are the speed relative to the ground? What is the direction relative to the ground? Picture. All right? Here's your boat. Your boat can travel 6.1 meters per second at an angle of 25 degrees up the river, okay, upstream. But the river flows 1.4 meters per second downstream. Okay? The combined effect of those two would result in your boat going like this, even though my arrow is a little curved, right? Because have we lined up our two velocity vectors tip to tail? Does the one start where the next one, or does the second one start where the first one ends? Sure, right? And then the combined effect, or the resultant, starts at the beginning of the first and goes to the end of the last. Okay? Now, in this problem, though, is this a right triangle? It's not, right? So in the previous problem where we had the train worker crawling or climbing on the side of the train straight up, the train moving straight sideways, we could just do Pythagorean theorem. But we can't do Pythagorean theorem on this triangle. But we've discussed that there is a way for us to handle this situation, right? Good.
SOHCAHTOA?
Well,
Law
we
of
can't
sine.
do SOHCAHTOA because it's not a right triangle.
Yeah, law of
right?
cosine.
So you could do law of sines or law of cosines, okay? But we talked about the idea that this boat, as it flows in this direction, right, it has components, right? It has a horizontal component and it has a vertical component. Do we have information to find those two components? We have the velocity of the boat, which is the hypotenuse. We know this angle right here, so we can use SOHCAHTOA to find the two sides. Right? We would do that for all of our vectors. So first, right, there's SOHCAHTOA for the boat. And you find the components of the boat's velocity, both horizontal and vertical. Okay? Here is SOHCAHTOA for the river. The river is on the y-axis. It's straight downward, right? Does it have any x components? If something's already on the y-axis, its x component is what? 0. Okay? So, now that we've broken everything down into components, what do? Add the x's and add the y's, right? We add up the x's, we add up the y's, and now you have an x component and a y component, and now you can use Pythagorean theorem to find the length of that side, and you can use your trig functions to find the angle. Does that make sense? This is no different. We would do this problem exactly the same way if, instead of this being a vector that represents 6.1 meters per second, if it was you drove the boat 6.1 meters, and then you drove the boat 1.4 meters, right? How we do the problem does not depend on the type of vector quantities. Whether they're displacements or velocities doesn't matter. You do it the same way. Okay? Does that make sense? All right, one last example. in the book on page 130, is question number 29 that talks about a pilot and his plane. So here's what I want you to do first. I want you to read the problem, and I want you to just draw me a picture of what the vectors in this problem would look like. Draw me a picture of what the vectors in this problem would look like. Okay? Talk to the person next to you. Draw me a picture of what the vectors would look like. Go.
So, you know it says the wind is pointed west? Okay, so I drew it like this, like here, and then the wind's going to west. Would this be the exact same distance east? Because you know how you have to point the plane this way?
Hold on a second. Let me try that. All right, so let's discuss. There are three things that we need to deal with in order to solve this problem. Right? What's one thing that we need to deal with to solve this problem? Okay. So we know that the wind, right, 65 kilometers per hour blowing from east to west. So I'm going to take this and I'm going to draw this vector to represent the wind. Okay? What else do we need to deal with in order to solve this problem? Okay. We know that eventually, right, the airplane wants to fly due north. So we know that there has to be a vector like this, right? What's the third thing that we have to deal with in this problem?
The fact that we have to go that way.
Well,
We end up at the
what other factor do we have to deal with in this problem?
ending place.
The 340.
The 340 is what, Julie?
The speed of the plane.
That's the airplane, right? So this plane can fly this fast. But what don't we know? What direction, right? Which one, so let me just draw this, okay? I'm going to draw, well, I'm not going to draw anything for the plane right now, right? Which one of these, red, blue, or purple, represents the resultant? Purple. Purple represents the resultant of this problem, right? Why does purple represent the resultant?
That's where they have to go.
It's what we ultimately want to happen, right? So, we said that our resultant has to take us from the beginning of the first vector to the end of the last vector, right? So if this is our first vector representing the wind, right, and our resultant goes from the beginning of the first to the end of the last, that then determines what direction we would have to fly the plane. Does that make sense? We okay with that? Now, we have a triangle. We know that this side of the triangle, is 340, because that's the plane itself. We know that this side of the triangle is 65, except I should write it in blue instead of purple. That side of the triangle is 65. What are we ultimately looking for in this problem?
The degree angle.
We're looking for this. Does that make sense?
Wouldn't the 340 only work if they specifically said the trip only took 1 hour?
No.
Because you're saying it's 340 kilometers per hour. So what if they went 2 hours? It's actually 600, or like, yeah, 680 meters traveled.
But you can't have a triangle that has two vectors with different units on it. You can't add meters and meters per second. You know what I'm saying? This wind is measured in kilometers per hour. So that means all sides of this triangle better be measured in kilometers per hour as well.
Okay.
Okay? Because you gotta have consistency within those vectors in order to add them.
Yeah, that makes sense.
All right, this is a little different than what we've done in the past, right? Almost all the problems that we've done so far, the resultant has been what part of the triangle? The hypotenuse, right? We already know the hypotenuse of this triangle, right? If we measured the plane flying, would we measure it to be 340 kilometers per hour in this problem? We said that this side, the purple side, represents the resultant of the plane flying and the wind blowing, right? What do we know about the hypotenuse of a right triangle? It always has to be the longest side. So with this combination of the way the plane flies versus the way the wind is blowing, is it going to speed up the plane or slow it down? It's actually going to slow it down a little bit, right? Because this side that represents the resultant isn't the hypotenuse, so it's not the longest side. Does that make sense? Okay. Now, they didn't actually ultimately ask us to answer that question, right? They asked us for this angle, okay? Now, in relation to this angle, what two sides of the triangle do we know? Adjacent and hypotenuse, right? So, what trig function are we going to deal with here? Okay. Cosine of theta relates the adjacent side and the hypotenuse of this triangle. But, are we looking for cosine of theta? We're just looking for theta, right? So we said when that's the case, we would have to take the inverse cosine of that side, right? And that means if we take the inverse cosine of one side, we've got to take the inverse cosine of the other side, right? So theta would be equal to the inverse cosine of the adjacent side divided by the hypotenuse. All right? And when you do that, if you do that, I believe not 89 degrees, you should get 79 degrees. Okay? So as far as relating this answer to the direction, right, going back to what we talked about here, if this was your plane, right, we would label this as 79 degrees north of east. If this is our starting point, I know that's not exactly where the starting point is in the triangle, but if you're talking about the plane, that's how we would label that angle. Okay? We okay with that idea? This problem would be no different if this was 65 meters and this was 340 meters. Okay? You can't mix them, but the process doesn't change just by changing the units. Okay? Good there? Alright. So, for the weekend, I know it's Friday, but so these problems, okay, the first couple up on the top, they're conceptual problems about adding velocities together and resultant velocity and stuff like that. These problems here are actual calculation-y kind of problems, including one that we just did right there, so got that one there. Okay? Questions? Monday we started on projectile motion. Woo!